Remember that all the flip-flop has this clock input. This is the way that we identify the clock. And then we have the Q variable, we're gonna work with Q only. The JK is made of a SR flow for the connection, but we're not interested in that at this point. We're interested in how it behaves. So we say that, let's say, 0, 0, 0, 1, 1, 0, and 1, 1. So if we have a value there at time t that we call q t, we have a value here at q t plus 1, we would like to know what is the value once we send a clock tick. Every time we send a clock tick, we're 1 time unit ahead. So this is q at time t, 1 clock tick, 1 clock tick. This is q t plus 1. Are you with me? Yes or no? So at 0, 0, what happens is that that's what it means. Is that clear? Okay. Now, if we send, this is like set and reset, okay? So if we set a 1 here, no matter what the value, what is the value there, 0, 1, we get a 0. And if we have send 1, 0, no matter what the value is there, we get a 1. Always. 1, 0, we get a 1. If there is a 0, we get a 1. If there is a 1, we make it. We input 1, 1, we're going to have what we had at this time inverted. So if we have a 0, we get a 1. If we had a 1, we get a 0. Are you following me so far? Yes? Silent means yes, or 10%?
10.
We try. I mean, if you are there, you sit there, and then at 7:45, and then I do a clock tick, which means I increase the clock to 7:46, and you are still there, the person in that seat is the same, right? That means if I do 0, 0, the same value remains. If it's 7:45, and then I turn the light off on, and you are not there, someone else, then the value changes. That's what we mean. That's what we mean with t plus 1.
Yeah, I wasn't here last Wednesday.
At 7:45. If we send a clock tick to the flip-flop and there is a certain input that is going to perhaps alter what is inside or the value remain. So when we say that a qt plus 1, which means 7:46 now, we're at 7:46. If we said at 7:47 we can have the same value that we have at 7:46, but we can have a different value. That those are the two options in a binary system, right? So qt plus 1 means that we get the same value. Let's say if I have a 0, jk, qt, I have the value 0, and I input 1, 1. What do I get at t plus 1? 1, right? And if I have a 0 and I input 0, 0, what do we get? And if I input 1, 0, and we have a 0, what do we get?
1.
And if I have a 0 and an input 0, 1, what do we get?
0.
Is that clear for everyone? Okay. So, we were talking about a counter with JK flip-flops. We're going to do an example with 3 of them. And this is the way we're going to connect those JKs. Here we have a 1. which means that always we have the 1-1 value on the J and K in. Initially, the value inside the flip-flop is 0. Then we're gonna have a second one, and the design we're gonna work with now is using practically the same connection all the time. What is the connection, except for the first one? Now we're gonna take this output back in, and we're gonna connect it with this one here. Through an AND gate. And then this goes into the two ends. And then we're gonna select another one. And then we take this output back in with this input. And so you see the connection is always, except for the first one that had a 1, all the others are the same. Take the output of the former one, bring it to an AND gate with the input of the former flip-flop and whatever it is connected to JM. All right? Then we need to have a clock input here. So that means that when the clock goes to 1, depending on what we have in the input, we get a result inside the flip-flop. Remember, these are, we're talking about memory, devices that remember. So we have this clock signal, let me put it this way. So this is the clock. So we say that inside the flip-flop, initially we have zeros. We're gonna send a clock tick. But before sending the clock tick, what do we have to see? What is the input, what are the input values for the first one on top? 1 and a 1. And for this one, we see 0, 1. What do we get? Oh, really? Now I'm getting 0, 1, 0, 1. So we have, in this case, 0 and 0. This one, we have a 0. What value is the output of this one? So we have a 0 here and a 0 here. What do we get?
0.
So what is the input of this one?
0.
0, 0. Okay, so the first thing we did was to set up the inputs. Now, what does it happen if I send a clock tick? Okay, we send a clock tick. What does it? This is QT. What do we get at QT plus 1?
1.
A 1 or a silence? If you don't see that we get a 1, we're in trouble. We'll have this kind of questions in the exam combined with another range. What is, tell me what is not clear. We say 1, 1, we flip. 1, 1, we flip. Do you understand what we're doing? This is a question in the next exam. We're gonna have questions about the control unit, about this counter, on the computer. So this has to be crystal clear. Tell me if you have questions, I can start from the beginning. Again. Questions?
So the last Q doesn't have to go back to the beginning for this one?
Why?
Like when we did the other flip-flop?
Well, you're talking about the ring counter that we did with D flip-flop. This is not a ring counter. That's another design. That's another type of ring. Questions?
No.
If you don't tell me what you don't understand, I cannot go in yes.
So this one counts like 1, 2, 3, right?
The idea is that this register is going to count 0, 1, 2, 3. And that's what we're gonna use this as program counter. Because every time we send a clock tick, it increments value. But we need to know how it works. So if I tell you, the same way we did in the first exam, give me a design using a counter, using JK to implement a counter and use a leaf flip-flop or something else, connect them this way. If you don't understand this, you cannot answer that question. So what is that you don't understand here? If we're having a series of flip-flop connectors in some way, we need to know what is the input. If we don't know what is the input, we don't know what is going to happen inside the flip-flop. And that's why we have to set up initially all the inputs. Yes.
So the name of this whole thing is a
Counter.
JK counter?
It's a JK counter register. Forget it about Googling, or because you're going to find a different design. And if I said, give me this design, and you give me the one that is in the internet, you get 0.
Question, more into clarification. So we're basically, in this example, the first input that we have is one at the top.
For the one on top, always get a 1, the 2 inputs.
So we always get that, we always start with the
Yes.
ones.
Uh-huh.
And so basically we are doing circuit and then we transition into Q, T plus one, because that's basically, remember that I told you I think about a cycle?
Remember, we're sending clock ticks.
Yes.
Because cycle is something that go back. Here we don't go back anywhere.
Right.
So far. The idea of QT, QT plus 1, QT plus 2, etc. Let me tell you something. Let me ask you a question. This is the value that we have now. The input is 1, 1. If we have 1, 1, what do we get? What's that?
If you have 1, 1, you get 0.
0. No, 1. You're right. Because we flips. This is the complement of what we had before. Let's say 1, 1 flips. 0, 0 remains. Let's put it that way.
Okay.
Okay, now, here. A clock tick. What is the value here?
0.
0. So when the input is 0, 0, the value remains. For instance, this one, this is 0, 0. What is the value of QT plus 1?
0.
0, 0. What is the value of QT plus 1?
0.
You see? But now that we are here, the input of this is 1, we know. But now we have a 1, right?
Yeah.
So the 1 comes here. This 1 is here. Now we have a 1 there, right?
Yeah.
So what is the input now for the second one?
1.
1 and a 1. This is a 0. 0 and 1 is 0. So this remains 0, 0. Now we're here. We did it already. We did this already. Clock tick. What does it happen? Flip, right?
Yeah.
This one is 0. Inputs 1, 1. What does it happen?
It flips 1.
This is 0, 0. Whereas 0 here, what is the new value?
0.
Why? 0, 0. 0, 0, what is it? 0, 0 remains the same value it had. Are you getting it now? Okay.
Kind of, yep.
So if we do once more, let's say this is 1, 1. Now, these are the one that we're going to use for the input. This is a 0. Come here. 0, 1, give me a 0. So this is 0, 0. This is a 1. A 1 is here. But this is a 0. 1, 0, 0, 0, 0. So now we have 1, 1, 0, 0, 0, 0. Next case. QT plus 3. Clock tick here. What is the new value?
That is 1.
Clock tick here. What is the new value?
0.
Why? 0, 0.
Oh, the value remains the same as 0, so 1.
Here. 0, 0. Clock tick. What is the new value?
0.
Okay. So look what we have here. we have 0, 0, 0, and this one. This one, we have 0, 0, 1. We read them bottom up. Here we have 0, 1, 0, and here we have 0, 1, 1. So we're counting 0, 1, 2, 3. So that's why we can use this JK flip-flop to create a register, which is a counter, and we can use it as the program counter in our computer. For instance, my goodness.
Did you write on?
No, this is an appointment for my dentist.
Did you write on? No.
Sorry. Okay, let me see what else. Probably another invoice. Okay, so now, if we have a computer and we say, this is the program counter that has a clock input, and this is a memory address register, which is made of different clocks. They are connected, could be several bits, okay, let's say 3. We just use one clock. And we're going to do this operation. Fetch. First, program counter goes into memory address register. Program counter is incremented by 1 because we get the value of the program counter to retrieve the instructions, and then increment the program counter to point to the next instruction for the next action. So we have these 2 steps. So there is a clock tick and there is a clock tick. Which one of these 2 registers receives the first clock tick according to this? Memory address register, because we come in this order, right? So this one. And which one receives the second one? Why? Because here we're copying from PC to memory address register. So the clock open the D flip-flop, get the value, and close. It's a latch. And then we send a clock tick here, but this one, which is made of JK, like this, just increments the value of what it has by 1. Yes, sorry.
So is the bus always active, but the data doesn't get written until it's?
You mean a bus? You mean the connection?
Yeah.
Okay, sometimes could be a bus, sometimes wire direct connection. Okay, the thing is that the value that we have when we have value in the program, that's an interesting question, very interesting. When we have a value inside this one, let's say 0, 1, 1. Okay? This is what these are the Q outputs. Remember, we have 3 flip-flops there. You always see this value here. So when we send this clock tick, the value comes in. And then when the clock goes down to 0, we close. No matter that you change this value. When you increment by 1, this could be incremented by 1 and get the value 1, 0, 0, but this is not going to change what is in the memory address register. Because we're using those registers as a latch. You clock 1, accept the value. Clock 0, block anything that is coming in. Is that associated to your question, right? Any other question? Okay, so this is, for instance, a register of 3 bits made of D flip-flop. We have to put it here, okay? So, if we would like to connect, if I say this is the memory address register, and this is the program counter, to connect these 2 registers, my goodness.
jump to record today.
Right. So in our question, the first clock tick comes here, and the second clock tick comes there. This one will open the D flip-flop to accept those values, because everything that is inside this flip-flop, you can see it in the Q output, that wire. And then the second click, what do we use this one? To increment the value of this raised by 1. Are you following me so far?
Yep.
Okay, you need to know how to create this one for 2 bits, 3 bits, 4 bits. There is a one for 4 bits in the book, in the lecture, in the book, and this is 3 bits. And we did 2 bits last time, the same thing. The only one that have a different connection is the first one, all the others the same thing. In the lecture, you will find that this last one has an AND gate for an overflow, but you can forget about it. Yes?
Is this the same as a ring counter?
Can you speak up a little?
Is it the same as a ring counter?
No.
Oh.
No.
What's the difference?
And what's the difference? Bounds are made of D flip-flop, and probably that is what your question comes in. A ring counter is something that makes a kind of loop. So a ring counter is something like let me do 3 bits again. A ring counter is this. Clock. So in the ring counter, what we do is move a value from here to the next, from here to the next, from here back to the beginning. Every time that there is a clock tick, you send the value to the next flip-flop. So they are made of the same type of flip-flop D, but you see that the connections are different. These are not interconnected. These are just connected in parallel with other rings. That would be it. Getting clear?
Yeah.
The ring counter, I mean, we can use flip-flop to implement different types of what we call devices. One is the ring counter that we use in the control unit. Another one is to use it to implement separate register like the accumulator, memory data register. There you have all those flip-flops making a unit, but they are connected in parallel to other registers. And in the ring in this case, we're using the ring counter inside the control unit. Okay? Now,
including the bonus points.
We submitted the exact same exams.
A lot of people says that kids grading is off, even if it's like the same answer to someone else, it'll be different regardless. It's what he feels. It's kind of stupid. I can check right now.
we're going to talk about the issue we have in control unit. So in the control unit, we're going to use a ring counter because in a computer we have the CPU, and there is a clock that is sending clock ticks to the CPU, specifically to the controller. And each time that the CPU receives a clock tick, it sends that clock tick somewhere else in the architecture. But then the control unit is a kind of clock distributor. Because he's receiving just clock tick and it's saying, this one goes there, this one there, this one here, this one there. It's just distributing the clock ticks that are arriving to the CPU.
I'm not
As we
sure.
said
I
before,
have to at least double check on the questions.
To first to T1, then to T2,
For 8.
T3, T4. I said last time that if we're working with 4 clock ticks in this class, and all the instruction work with 4 clock ticks, I have this T5 to explain that you can have instructions that need more clock ticks, but it's not related to the questions we're asking or answering today or in the exam. In the exam, if you answer the question and you give me this line with a T5, you get 0 in that question even if everything else is, well, it's good. Because we have 4 clock ticks, we don't need to have extra clock ticks there that they are doing nothing. Okay? Because that's what it tells me that you don't, perhaps, I don't know if you understand it or not, but if you include T5 because you are just copying something that you don't understand. So remember, only 4 clock ticks. Now, what are we saying here? This is fetch. First, we send the content of the program counter to the memory address register. These are register. This is made of JK flip-flop. This is made of D flip-flops. When we send this clock tick, that means that this register is going to affect what is in the input. This is exactly what we were doing here. We send the first clock tick to the memory address register to copy what is in the output of the program counter. And then we send the second clock tick to the program counter to increment it by 1. Here we have it at box level, let's say. First clock tick coming to the memory address register, so we copy what is in the program counter. Second clock tick, increment the program counter by 1. These are JK flip-flops. Clock 3. Remember that memory is like an array, and this is the index. So this is pointing to a memory location, and what we have in that memory location gets into the memory data register. And it is an instruction. Okay? And then to get it here, we need the clock 3. And then we said that when instruction register, which is this one, that means reset the instruction register. Put it into, no, I'm sorry. We are in fetch, right? So when we get here, we get a new instruction into the instruction register, and then we get, for instance, load, which is this line. Remember, we have this line and then this line. So we start with the sequence to execute load. Copy what is in the memory, in the address of the instruction register address into memory address register. Access memory and the value of this is load of the store. Yeah. So we send the value from memory address register, from instruction register to memory address register to access memory. The second clock tick gets here to get something, a data value from memory. The third one goes into the accumulator because we're going to copy what is in the memory data register into the accumulator. And then the last one is instruction register reset to go back to fetch. Fetch, execute. Fetch, execute. This is another instruction, okay? In this case, we have this there. Sorry, this is another instruction, jump, and this is a store. So pay attention to this, because another error that people make in exam is that they say store and they connect it here, and that is wrong because each instruction has a different binary string: 0001, 0001, 0011. So if I say, let's say, store, which is 0123, and you connect it into 0, that is wrong. That simple detail makes the instruction, the sign, that it doesn't work. It's wrong. So you have to take care of this. If I I say jump, you have to contain number 7, which is jump. Right? Let me go back to this is lecture 2 where we presented the architecture of the time machine. And in that architecture, we presented this is the machine where we do fetch, copy the program counter into memory address register, set memory, get the instruction here, and send it to the instruction register. Then we have load, another sequence. This fetch execute cycle. This is part of the computer. Copy memory into memory address register. Now we can say this program counter is made of JK flip-flops. Memory address register is made of D flip-flops. Memory data register is made of D flip-flops. Accumulator made of D flip-flops. Even this one, okay? Instruction register. So this is the fetch cycle. So we access memory and the value gets here, and from here, we get the instruction into the instruction register. Once, then we send the opcode into the decoder to select one of the output and execute one of the instructions. That's what we're doing now. We're talking about the details of this computer. And then we have the opcode that goes into the decoder here, which execute. And this is the fetch cycle, but here we're doing five steps. We say program counter goes here, increment the program counter, get the instruction from memory to memory data register, and send it to the instruction register. We included at this point, at the beginning of the semester, that the opcode have to go into the decoder because we didn't know anything about the decoder. But now we know that once the instruction is in, just give me a second. We know once the instruction is in the instruction register here, and the bit is the input of the decoder, and we select one of the output lines. We know that, but at the beginning of the semester we didn't know. So we know we have to say well that goes to the decoder. Alright? And then we have load, add, store, okay? And then halt, just stop the machine, in this case. But if we go to the control unit presentation, oh my God. You see that we have jump here, number 7, and we select. What do we do in jump? We copy the address register in the program counter. So we're not going to execute the next instruction, but the one that is the jump operation service. Say, what is the address of where when I store in the program counter? It's like when you have the loop in Marie, that you load a value, add a store, load the subtract, and you check escape or not. If you do not escape, you do jump mode, you go back. To do that, that means that we copy the address into the program counter to go to anywhere in the sequence of instructions in the program. And then jump only need to execute this step, and then reset at the end to go back to the fetch cycle. And all the instructions in our computer takes 4 steps, 4 clock ticks. So we need to have these two as not operation. Because if we make this in 2 clock ticks, then the clock tick is not going to be synchronized for all the instructions that have to start with the T1, T2, T3, T1, T3, T4. Okay? So, the last exercise we did last time was to include the control unit here. This is the control unit. The ring counter here. And I told you to create this design with the ring counter for all these instructions. This is the best way to study for exam this coming Monday. All right? Questions? Yes?
Did we learn the add command in Recoder?
Monday.
I told you to do add and we discussed it today.
Yeah.
Any answer? The add instruction to implement it? No one? Okay, let's see what is the sequence for add?
For the 5th or
We're going
Wednesday.
to add two numbers. The sequence is this. We take the instruction register, we have one of the values in the accumulator. Instruction register address is sent to the memory address register to access the other value. Then we access memory.
Okay, great.
Thank you. We access memory with this address and get the value in the memory data register. Now that we have the value there, we're gonna take the contents